At NeurIPS this year, we saw a renewed focus on grounding AI in the real world, with figures like Fei-Fei emphasizing the importance of embodied intelligence and spatial understanding. As researchers, we're all keenly aware of this shift and the need for robust spatial intelligence in our models. Now, a new paper on this topic just came out, offering exciting new avenues for potential high-impact research. Thinking in Space by a team of leading researchers from NYU, Yale, and Stanford explores how multimodal large language models see, remember, and recall spaces. It proposes to formally define and benchmark visual spatial intelligence and evaluates a wide range of multimodal large language models to obtain some key insights. Let's walk through them together. Humans navigate a 3D world seamlessly. For example, we can mentally reconstruct our kitchen and recall what it's like, where the fridge is, or how to find the coffee cup even if we're not looking at it. We use visual spatial intelligence in this process, and it involves recognizing objects, estimating distances and directions, and switching between perspectives. The core question here is that can multimodal large language models develop similar spatial intelligence? We will follow the authors to first define what visual spatial intelligence is, and then look at a new VSI benchmark and some very interesting findings by evaluating some popular large models on it. And lastly, we look at possible ways to improve the visual spatial intelligence for large models. In the paper, visual spatial intelligence is broken into 4 pillars. First, visual perception, the ability to recognize objects or areas from egocentric viewpoints. Second, linguistic intelligence for handling instructions or logical text-based reasoning. Third, temporal processing for extracting continuous context from sequential video frames. And lastly, spatial reasoning. This is further divided into relational reasoning and egocentric allocentric transformation. Relational reasoning addresses reasoning about relative configuration. For example, who's closer, the TV or the window? Is the soda can smaller than the fridge? Egocentric allocentric transformation is the ability to build a mental map of the entire room. The allocentric perspective from first-person camera frames. To test these capabilities, the researchers created a benchmark they call VSI Bench. It has over 5,000 question-answer pairs. It is derived from 288 real-world indoor videos such as apartments, labs, and factories. The videos are pulled from 3D reconstruction datasets like ScanNet, ScanNet++, and ARKit scenes. The authors propose 8 tasks grouped into 3 categories. The first category is configurational tasks. This includes object count, relative distance, relative direction, and route plan. The second category is measurement estimation tasks, which ask to estimate object size, room size, and absolute distance. The third category is spatio-temporal task, specifically about appearance order of objects in the video. Feel free to pause the video to take a closer look at the example question for each task. Each question is either multiple choice or numerical, which are measured by accuracy or mean relative accuracy, respectively. The team evaluated 15 multimodal large language models, including proprietary ones like GPT-4 and Gemini, and open source ones such as Lavinex Video and Interview 2. Each model sees either the entire video or a subsampled set of frames, receives the question, and produces an answer in a zero-shot fashion. A quick glance of the results are shown in the table on the right. Now let's take a closer look at the key findings. First of all, humans outperform large models. This is not surprising. Humans have years of experience in understanding the physical world spatially, but the models are only trained on mostly 2D digital data, like internet videos. Second, it's the usefulness of vision in these tasks. Removing the video input often drops performance below random guessing. While these large models still lag behind human in leveraging visual data, they do display emergent strengths. For instance, they're sometimes decent at object size estimation. Perhaps they've learned common size and proportions from general training. And lastly, we see the large models especially struggle with tasks requiring lots of relational reasoning. The authors do an error breakdown on one of the best performing models, Gemini 1.5 Pro. They classify mistakes into visual perception errors, linguistic or logical reasoning errors, relational reasoning errors, and egocentric allocentric transformation errors. The last two both belong to spatial reasoning, and they make up for more than 70% of all the errors. Think of it like the AI focusing on local details, but failing to build a global map. It's akin to someone rummaging around a dark room with a flashlight, seeing objects clearly, but missing the big picture. Of course, we would like to see what's the model's internal reasoning. The researchers used two types of probing: the linguistic probing in the form of self-explanations, and the visual probing of drawing cognitive maps. For self-explanations, models are asked to explain their answers step by step. In some successful cases, the model reference timestamps and show understanding of an internal world model. In other cases, it can get confused because of perspective shifts. In visual probing, the models are asked to produce a 2D grid showing object centers. Something noteworthy here is that the large models did surprisingly well locally. For example, it knows the table is next to the chair, but they struggled for global layout. The little clusters of correct relationships are not tied coherently across the entire map. Researchers also tried ways to improve the model. Chain of thought prompting is known for helping large language models solve reasoning tasks by breaking things down in language. This work tested zero-shot chain of thought, self-consistency, and tree of thoughts. Surprisingly, these hurt performance on VSI benches by spatial tasks. It seems like that the high-level verbal reasoning confused the spatial sense. It kind of makes sense. If you imagine describing a painting purely in text, you might end up tangling details that break the overall geometry. However, when the researchers explicitly asked the model to produce a rough floor plan first, essentially forcing it to reason in a more visual or structured way, performance improved in distance questions by up to 10%. This suggests that combining a structured spatial representation or cognitive map with standard textual inference might be the next step forward. So, what's the takeaway from thinking in space? Multimodal large language models show some promise in seeing and recalling certain aspects of environments, including object categories, approximate sizes, and local relationships. But they fall short on global spatial consistency and are not great with rotations, route planning, and perspective transformations. Standard linguistic prompting might not cut it for geometry-heavy tasks. We might need more visual or embodied training, specialized map building modules, and visual spatial prompting techniques. I think this paper is a timely reminder that while AI can already do incredible things, truly mastering visual spatial intelligence is still a frontier challenge. That concludes today's paper review. See you in the next one.